Yeah, so our next speaker will be Zabludoff, talking about QPE Host Galaxies. So.
Actually, I'm not talking about QPE. I was inserted here because I'm not making the end of the week, so I really appreciate. I'm kind of crashing the QPE QPO party with much more of a talk about TDEs and their host galaxies. However, I did want to start with a relevant screen that's going to connect to the things that I emphasize about TDEs today. And that is, it's very early days for understanding what kind of galaxies host QPEs and the other variants that we just heard about from DJ. These are legacy images. There are a couple of HST images for 2 of these. We've mentioned 1 or 2 other.
It's just a TV that turned off automatically.
Okay.
Oh, it was a little box.
And this is the state of our knowledge.
Perfect time.
Perfect time.
Ricky just mentioned to me, like, you need to press a button.
Well, now we know.
No,
So a couple of things I wanted to stress is it's very difficult to tell what's going on from images of this quality. There appears to be a morphology of galaxy types. But if there is an implicit connection between tidal disruption events and QPEs, then there should be an implicit connection between the types of galaxies that tend to host TDEs and QPEs, which are post-starburst galaxies. So we should keep that in mind. We should be thoughtful of that when we're talking about the potential studies of host galaxies for QPEs. There have been some claims, we heard it earlier, that there's some unusual representation among QPE host galaxies in so-called warm or strong, E+A, post-starburst galaxies, pick your favorite designation. I would caution on that because, as we also discussed earlier, all the QPE host galaxies are very nearby. And there are selection effects associated with that we talked about earlier, but also the fact that when you are studying the spectral characteristics from data limited to within, for example, a Sloan fiber, then you are literally studying the galaxy on the scale of smaller than my finger in this picture. And it is very easy to miss emission from the galaxy extended beyond the core. And so classifying things as having had a post-starburst history or not being actively star forming or things like that is problematic right now until we really hit them hard with long slit data or IFU data to understand the galaxy fully, which is something that we're working on, several people in the room are working on. So I think the jury is still very much out. There is an indication. You know, these are the 5 I had before I came to the meeting today. There is an indication of some shells in at least one of these sources. That would be a fairly high fraction. Whether or not 2 of these out of the 5 have a post-starburst history, I think we should wait on. If that were true, that would be a disproportionately high fraction and potentially interesting. The shells might be indicative of some recent galaxy interaction. I'm sorry?
What do you mean by shell?
Shells in the stellar distribution. So you can see there's some low surface brightness features here extending beyond the galaxies that have some asymmetry. And there's some resonant areas that are lit up by a concentration of stars that may indicate some sort of tidal interaction. But again, it's hard to characterize the others. There's also something I think going on towards the core of that one, but we're looking into it, particularly my student son.
Which one is it? Can you say which one it is?
Yeah, so both of these are HST observed galaxies. This is what is it?
RxJ 1301.
RxJ 1301. Okay. So it's a very interesting question. I hope we'll maybe get some clarity during this meeting of possible potential connections between TDEs and QPEs. I think that's linked to the question of what evidence there might be for TDEs arising in black hole binary systems, whatever the appropriate ratio of masses is there. Are they enhanced in such systems? Especially if there are interactions or mergers between galaxies, we would expect to be creating black hole binary systems. We would be expected to create black hole binary systems of very dramatic mass ratios, just statistically. It should be very unusual to get comparably massive parts of black hole binaries. We'd like to understand how often, if ever, tidal disruption events occur while galaxies are actively forming stars, and particularly in the starburst phase of their evolution. That's not really been seen very much, either in X-ray detected TDEs or optical TDEs. We'd like to understand why we don't see tidal disruption events much in red dead spheroidal galaxies. The place we do see a lot of tidal disruption events, a disproportionately larger number, are in between those two phases, between the time where a galaxy is starbursting, possibly due to some interaction with another galaxy, and the time several gigayears later where it's red and dead. We'd like to understand why some are X-ray bright, when others are optical or UV bright. Almost every tidal disruption event host galaxy, and the types of galaxies that generically tend to be favored by tidal disruption events end up in the liner or Seifert-2 part of the EPT diagram. We'd really like to understand the connection between having some kind of active source and the presence of these objects. And another thing I'm really interested in discussing, which I won't be discussing today, is the models that were developed by my former student, Sixang Wen, the slim disk models, to model the X-ray continuum of tidal disruption events and potentially constrain the mass and spin. Okay, so let me get down TDEs, not QPEs now, although I will try to sprinkle this comment, QPE related comments throughout. So one huge question is why tidal disruption events on scales of parsecs or subparsec scales favor galaxies that tend to have particular unusual star formation histories on kiloparsec scales. So when we talk about the host galaxy properties, we're talking about the whole galaxy and its star formation history and what it may have experienced in its interaction with its environment. And yet this is kind of reminiscent of the black hole mass galaxy bulge mass relation, where you have this enormous range in physical scales, and yet they know about each other. We really like to understand that. And just to remind you, instead of looking at the properties of TDE spectra now, what I'm showing you are optical spectra of the host galaxies of TDEs, taken in many cases before the TDE went off. And one thing to notice here on brightness versus rest wavelength is these are very weird spectra for host galaxies. And what I mean when I say that is they have very strong Balmer absorption lines. They do not have strong nebular emission lines. The story that tells is they are dominated by an astellar population that's about a gigayear old. There was a burst within that time frame in these galaxies, but they're not forming stars anymore. They don't have H alpha. They don't have O2 in emission. So these are galaxies that are in transition between star bursting and the other kind, okay, the ones that have stopped. And that was something that was pointed out by Yair Arkavi. And I've been studying those galaxies in other contexts for a long time. And so we've been collaborating ever since. My student, Deco French, put together, we've seen this diagram for QPEs already today. Characteristic plot, again, the optical spectrum of the host galaxy of that H alpha emission versus a Balmer absorption line strength. So you can think in this case of this plot indicating current star formation increasing along the y-axis in the host galaxy, recent star formation increasing along the x-axis in the host galaxy, meaning that quiescent red dead galaxies, and by quiescent here, I mean not forming stars. I'm not talking about nuclear activity, okay? Red dead galaxies here, star forming galaxies go way up past the top of this plot. And this very interesting spur to the right, which we've already seen in an earlier context of post-starburst galaxies, the ones that aren't forming stars now, but did form a lot of stars recently within the last gigayear or so. And when we actually look at the position of tidal disruption event host galaxies, as Decker French did in her paper, and this is what we had to work with at the time, but these numbers have held up, you can see that they are not a random selection of the gray dots defined by the Sloan sample in this plot. They do tend to occupy that spur at some enhancement. That's pretty significant. And this is true within this range, depending upon whether they're X-ray selected or optically selected. I'm not saying they're the same TDEs, but they all seem to love post-starburst galaxies. So it's really worth understanding a little more about post-starburst galaxies and what the role may be in this. And as I said, if you want to stipulate a connection between QPEs and tidal disruption events, you have to become a fan of post-starburst galaxies as well. Okay, so why do they end up favoring these galaxies? I'll get to that. But we know that, for example, in this cartoon of the evolution of a potential sequence that would have a moment where a post-starburst galaxy would occur, we have galaxies crashing together. We can argue about the mass ratio of those two galaxies. It could be a wide range of mass ratios. They create a burst of star formation. There may be a phase of winds. These are not 0.1 C winds. These are winds of hundreds of kilometers per second. That post-starburst phase may end, producing a post-starburst galaxy. This is where we're detecting all our TDEs, go figure. And then eventually you let things settle down long enough, the gas, the dust go away, the stars that were made recently die, and you end up with a red dead galaxy. That's a cartoon. And one question that's natural to ask, and that I alluded to at the beginning of the talk, was, is this phase the special one? Could TDEs occur anywhere along here in the host galaxy? Or is there something very, very special physically about this moment in time that enhances the TDE rates? And as I mentioned, we don't see TDEs at this point in the sequence. There's been a claim of one TDE found so far or so in this part of the sequence. Why here? Is it something we'd like to understand? And the other thing that I wanted to point out is that if we look at the distribution of post-starburst galaxies defined by the contours here in the Sloan Digital Sky Survey, as a function of the fraction of stars that got made in a burst and the time since the burst ended along the x-axis, and we compare the few host galaxies of TDEs for which we can do this analysis at this time, this is going to grow by factors of 10 or 100 in the next few years, which we're very excited about. There are a couple of interesting things. This is just the post-starburst phase. So we're just picking apart that one frame that I showed you earlier and asking the question, is there a pileup at either boundary and time? How different are they from general post-starburst galaxies? And what you see here is a spread in the times elapsed since the starburst ended. That's real physically and not that different from the distribution of Sloan galaxies. So even within the post-starburst phase, they don't appear to favor a time. Okay, so How do PostStar, I'm gonna go through this very quickly. I'm happy to talk your ear off about any of these points later. I'm gonna start with the things we know about the kinds of galaxies that host tidal disruption events and move on to the things that we're far less sure of. But how do they form? What do they become? Why does the starburst stop anyway? What's the connection to feedback? In this case, having to do with winds arising from the nucleus or winds arising from the evolution of the stars in the galaxy. Do they shut down the star formation? Could they gas be associated with tidal disruption events themselves? Open question. Why do tidal disruption events favor this phase in the evolution of this sequence, apparently? And could we use this preference for classification? As you all know, Rubin Observatory LSST is going to be coming back with 10 million alerts per night. 1 million of those are going to be real. Probably 500,000 of those, hundreds of thousands of those are going to be extragalactic. We have 500 telescopes in the world capable of following them up. If everybody is awake and ready to do it that night, how do you down select? That's a big question. If you're interested in tidal disruption events, they are not going to be the dominant part of those alerts. So you really have to be good about finding them. If you know they prefer certain types of galaxies, yes, it's biased, but you could find a lot by knowing in advance where the post-starburst galaxies are. And if a transient happens in one, then maybe you should divert some telescope time. How do they form? Short answer is there's a lot of evidence for galaxy-galaxy interactions and mergers. That means there's the potential for supermassive black hole binaries to form. We see tons of evidence for shells, tidal features, close companions, disruptions in these galaxies. And I should point out some recent work that I'm doing with Mary Putnam and my student Young Sun again, where we've now pushed down the mass function for host galaxies and post-starburst. So typically we were really looking at what you would consider to be, Milky Way analogs or brighter. Now we've pushed down below the LMC. So we're in the regime of lower than 10 to the 9.5 solar masses for the galaxies. And we are finding post-starburst, post-merger galaxies in the Sloan sample. It's harder work, but if you look at them, some of them have very clear signatures of interaction. They have the same history. Now, why is this interesting from the standpoint of tidal disruption events? Well, if you see that a dwarf galaxy has merger signatures, it's merged with another dwarf galaxy. The potential exists for you to have an intermediate mass black hole. So if you take the galaxy bulge mass relation and ask what kind of black holes these galaxies could harbor, you easily get down to 10 to the 5th solar masses, and we can push even deeper than that. So these may be the galaxies where you might get excited if transients get discovered, because they're potentially tidal disruption events that could arise from intermediate mass black holes. And from what we've learned, if there's no bias, observational bias, they also might be more likely to have QPE in them as well. Okay, gas-rich galaxy-galaxy interactions of some kind. This sequence is viable, that's why I put it up there to begin with, to produce this phase. What do they become? Do we get one of these? What's the observational evidence? I waved my hands about it earlier. I'm going to only slightly wave them less now. Happy to talk your ear off about it, but in every way that we can possibly measure, these are galaxies destined for red deadness. We've looked at their morphology, and they're bulge dominated. They have power law, early type profiles, which are indicative of what's expected for galaxies that are interacting. They have their own fundamental plane. It's just that they're brighter right now than red dead ellipticals, but that will evolve in a few gigayears into the elliptical fundamental plane. They have positive stellar population gradients. They're bluer in the center than they are in the outskirts. It's the opposite of red dead galaxies. But if you evolve the stellar populations that we've measured over this 1 to 2 gig a year period in the future, and they have star clusters. They have bright blue star clusters orbiting them that are very much consistent with populations of starburst galaxies and would be consistent in a few gig years with evolving into early type populations. Again, we've done the modeling for all this, but I'm just waving my hands right now. So this step's okay. There is a sequence here that they play a role in. How do they get, though, from the previous frame in the movie to the post-starburst phase? Why do they stop forming stars? They had to have had a lot of gas to be making a big burst of star formation. It's kind of hard to shut that down. How does that happen? Well, we found a lot of molecular gas in these systems looking at them with ALMA. That molecular gas tends to be concentrated in the central 1 or 2 kiloparsec of the galaxy, much more so than the stars are concentrated. But it's there, and it's there in a mass fraction that's very consistent with galaxies that are still forming stars. This really threw us when we first observed this. In fact, we didn't first observe it with ALMA. We first observed it with less powerful telescopes, but it's confirmed with ALMA. And why are these galaxies not forming stars then, if they still have these huge reservoirs of CO gas? Is something supporting that gas against collapse and subsequent star formation? That's maybe the feedback connection, okay? Well, what do you get when you look for denser gas, the kind that you expect to form stars? Even the theorists among you, you don't see it. They're not, it's not detected. HCO plus, HCN are not detected. There isn't any dense gas. That's why they're not forming stars. Yet there's a ton of CO. Why isn't the CO collapsing as a tracer to make denser gas? Something supporting against a collapse. We have a lot of evidence that the CO is disappearing in these galaxies over time. We actually can measure time with these galaxies. That's a whole other talk, but I'm happy to talk to you about that. But why no new dense clouds? And that's where the idea of something energizing those clouds, pushing those clouds out against collapse. Is it heating them? Is it, creating a different density? What is it doing? It's not that stars are consuming the gas over time. It's something's holding the gas up against forming denser gas. And what we see if we actually look at a plot of the detection of outflows, and now I'm talking about outflows measured from the sodium D line. These are optically determined outflows of hundreds of kilometers per second. What you see is across this sequence with the post-starburst in the middle, that our ability to detect outflows in these galaxies diminishes. There are fewer. Also, the average velocity of the outflows goes down. So the winds are diminishing across the sequence. And even within our post-starburst sample, we see a diminishment in these winds over time. But what's interesting about them is the time over which the winds decline is a lot slower than the time over which the star formation declines. They're decoupled. And that starts to suggest that it's not stellar evolution that's driving these winds. The stars are evolving to quiescence much faster than the winds are. So is that a potential smoking gun for nuclear feedback? We're analyzing this, but I think it's an interesting question. And if you actually look at outflow speed versus escape velocity for the sample, there are quite a few objects that exceed, even in the projection of their velocity along our sight line, exceed the escape velocity as a lower limit. And in fact, exceed the escape velocity for the circumgalactic medium even. But the ones that do have AGN in them. So here we're seeing our fastest outflows being associated with host galaxies that have no AGN. So again, there's a connection of feedback perhaps with nuclear source. We don't know whether these had tidal disruption events, will have tidal disruption events, but there seems to be energy coming from the nucleus. Okay, where the winds originate? Great question. If we could show they came from the nucleus, that would go a long way to actually solving this problem. We're looking. What do they do to the galaxy? That's really what we mean when we talk about feedback. It's not having winds. It's having winds that actually change the history of the galaxy. We can make that connection. And I will start wrapping up. Thank you. Okay, I will talk a little faster. Why do tidal disruption events favor these galaxies? Some of the people in this room have proposed different models for this. I already mentioned these are systems where you might expect the formation of a binary black hole. It's certainly consistent with the idea that you could enhance tidal disruption event rates. There's also, as Brian and other collaborators have pointed out, the potential to have anisotropies in the orbital distributions, which happen when you merge galaxies together. That could also feed the monster more efficiently. And then you could just concentrate the gas in the collision of galaxies, it's dissipative, into the core, create a burst of star formation there. We know that's where the new stars reside, and enhance the density of the core to the point where you're more likely to have a tidal disruption event. Where are we on all these? Well, there is certainly evidence from stuff we did with Grau that he wrote up of an enhancement of the central stellar surface density. If you look at the velocity dispersion of the host versus the central stellar surface density, this is not on the parsec or subparsec levels. This is still kiloparsec scales, take it with a grain of salt. Nevertheless, compared to Sloan galaxies in the contours, there seems to be an offset to higher stellar density. So that is still a viable model. It's also interesting that if we look at the question of black hole binaries and what we would expect, we could actually map the age since the starburst began and assume that try to estimate the highest mass ratio binary that could have time to coalesce since the starburst began at the merger. And you can see that along the top axis, and you can see the time distribution for our host galaxies for the tidal disruption events. Now, what's interesting here is most of them are within 600 mega years of the start of the starburst. That translates into very equal black hole mass ratios, 10-to-1 or so or higher. And that's a little weird, right? Because most mergers should occur with much more wildly discordant merger ratios. So it seems like if the black hole binary is upping the tidal disruption event rates, that is very sensitive to having roughly equal mass mergers or more equal mass mergers than you would statistically expect, or the binaries aren't a driver. So I think we need to do a lot more work on this kind of question, and there are lots of assumptions involved in this. Okay, lastly, I would like to point out what I did before, which is that no matter why tidal disruption events prefer these host galaxies, it's an incredibly useful tool for classification, and that we know where a lot of these post-starbursts are already, even before LSST gets on the sky, and therefore we know which potential transients are going to be interesting from our perspective. And in fact, we've done a lot of work on machine learning and neural nets. This was work done by these two students here, Chia-Lin Ko and Marina Kisley. And even from the properties of the host galaxy, even if all we know are the photometric properties of the host galaxy, we haven't even classified them post-starburst. We just know they're green, for example, on average in their integrated starlight. We do much better than random. TDEs are only expected to be 0.4% of common alert streams once you down select a little bit. And we get 1 out of 7 right. That's going to save a lot of telescope time. And that's just from our pilot study. We're doing even better now.
What's the rest of the alerts mostly coming from?
Yeah, where are the rest of the alerts coming from? All different kinds. Once you're into the extragalactic space, and once you've excluded AGN, mostly type 1A and type 2 supernovae, we can do much better than random for them too. Again, just knowing the color of the host galaxy, this is kind of blowing me away at this point. But it's actually, we're doing way better than the monkeys at the typewriters right now. The reasons that we have to interrogate the models to understand there are physical connections here that are interesting. Okay, so let me quickly finish by going back to the questions I asked at the beginning and just highlighting what it is we think we know about the kind of galaxy that hosts tidal disruption events and maybe a factor with QPEs as well. And that where are tidal disruption events relative other than in fate and in favoring these galaxies? There's this question of black hole binaries, which is a very interesting one. What are the signatures in TDE spectra for black hole binaries? I mean, we might really be looking into that, among other things. The feedback connection, indications it might be nuclear. Is it related to TDEs more directly than that? We have various lines of evidence suggesting why TDEs are favored by these systems, and we can use them for classification. We can use this connection for classification. So thank you very much for your attention. I love it.
Just a quick thought. So you're talking about why do TDEs favor these E+A galaxies, and there's many different ideas, but many of them, in fact, share the idea that either if you're forming new stars, within the lost cone, or you're generating anisotropies that are pushing existing stars into the lost cone, that the lost cone is fuller than it would be in the standard steady state thing. And so in addition to just the rates being enhanced with a fuller lost cone, the distribution of properties will be different also. And in particular, people talk about penetration factor or angular momentum. You'd think you'd have a higher distribution of high penetration factor TDEs, and also I think more inclined TDEs.
Yes,
And so it'd be interesting to see, I mean, those things are not directly observable,
right?
But it'd be interesting to see if
those were correlated with the
and
stellar
if the not
concentration.
just are the rates higher in E+A
Right.
galaxies, but are the properties more reflective of a fuller lost cone.
I think that's a great point, and I think one could potentially do that because some of the models we're working on will put a constraint on orientation, put a constraint on some of the issues you mentioned, and we will have enough where we'll be able to ask the question, are the ones in galaxies that clearly have had this recent merger activity and starburst implicitly different in their properties than ones out elsewhere? I mean, one other thing I should mention is we have a very bisample of post-starburst galaxies, E+A galaxies, whatever you want to call them, period. Because most of them, they're rare. So you need a big survey to find them. And big surveys come from fiber surveys. And fiber surveys are only sensitive generally to the center of the galaxy. There are lots of post-starburst galaxies that if you consider the whole galaxy, have all that post-starburstiness outside of the core. And they're completely ignored in the types of selection that I'm talking about. So if you actually go back to spatially resolved data, you see can be almost half of or a third of galaxies with post-starburst signatures where this history of the galaxy spatially is very, very different. You actually end up with a late burst of star formation in a ring or at large distances from the center instead of this concentration. And whether those are the product of mergers, is still quite up in the air. That seems to be a different history. Whether those have tidal disruption events, we don't know, but that would be a case where you're not concentrating in the center.
Right, that'd be really weird.
Yeah, that would be really weird, right? Yeah. Yeah, Brian?
I was going to ask what we know about for these post-starbursts in terms of whether other galaxies, most galaxies go through this phase. And I guess it relates to the question of, do we expect TDEs to to expect the black holes and TDs to follow the, for example, M sigma relation?
Right.
Or do we expect them to be deviants from that for some reason? Because this kind of relates to how
It's
we actually
very
get black
critical.
hole masses from these galaxies where we're seeing TDs.
I completely agree. I think that's a huge question because when you have galaxies that are recently merged, those galaxies can definitely lie off the black hole bulge mass relation. And they can do it, in a way that exceeds the current scatter. So I think we have to be cognizant of that. And I think modeling will really help in that regard because I think to within, factors of the scatter in that relation, if you take the extremes, you might still be okay, but they're not going to lie on the relation during this, several hundred mega year period.
And there aren't many, or if any, the E plus A's that have dynamically measured black hole masses are very few.
Yeah, because they're a mess, they're train wrecks.
They're train wrecks and
Yeah.
also they're just, you can only do that for
Right.
handfuls.
So that may be a place where you turn it around and you say, okay, I'm going to use the total disruption event to get that, but you have to buy your model then.
I
Yes.
have to believe one.
Yeah, yeah. But you have multiple ways potentially of measuring the mass at least, if not the mass and the spin. And I think that's only going to get better.
So I guess just to follow on that, you can calibrate whatever model you have for non-E plus A TDEs and then use it for T plus TDEs to get the mass, right? Does that make sense?
Sorry, so you're suggesting that
saying
you
that we-
take the standard black hole bulge mass relation.
Yeah.
And then the question is, where would these galaxies lie on it? And if you naively apply, a way of calculating the black hole mass, they will scatter. There are very few measurements of that though. And you'd expect from models that they'll scatter a lot about that relation.
I think the thing to maybe do is look for where there's AGN measurements and those sorts of galaxies or similar galaxies, although there's
So here's the catch 22. At least in the post-starburst galaxies, the ones that have had tidal disruption, we select against strong AGN by definition because we don't want there to be emission lines.
yeah.
So there are cases where we know there's been a recent starburst and there is a strong AGN, but we'll throw those out and they don't seem to have harbored at least the tidal disruption events people have looked at before. So that's where you get
Yeah.
into a hard problem with determining a mass distinct in a different way. Maybe use iron K alpha. I mean, there are potentially other techniques we could bring to bear, the X-ray community could bring to bear, I think.
Yeah, so another question is, I don't know about starburst galaxies, but maybe you tell me if there's an answer to this. But do we have like a volume limited sample of all the starburst galaxies at a certain distance from us?
Yeah,
And what is that
I
number?
don't think we've always had a magnitude limited sample. You could construct a volume limited sample, but it would not be large.
So what are the numbers? Like, let's say less than 0.1, how many? Because I'm thinking,
They're about 0.2%. It depends on how people select. Based on the box that I showed you from the H delta H alpha plot, they're about 0.2% of galaxies in the local universe. It's a factor of 10 higher at high redshift because you have a lot more interactions in gas.
is it practical to like target some of these and just like look at them, continue, like, is that even feasible?
So this was something Yair Arkabi was doing with the Kate array for a while, is just monitoring. I think now it probably makes more sense to just use ZTF or let LSST do its thing and then go backwards and say, figure your rates out from the post-star bursts that are included there. But I think that's, I think it's going to be a very different era in a few years. We're going to learn a lot more. And Brian, you had another question about how common the sequence is, and I was trying to make sure I responded to that. You had asked me two things.
Oh, yeah, I guess it was kind of connected. It was just like, do we expect,
Galaxies.
I mean, if
to
all
go through this.
galaxies go
Right.
through this path,
Right.
then, maybe we don't expect significant deviation. I mean, as you said, if the way you get on M sigma is by then swallowing the other black hole and
Right.
then some feedback, and so maybe these are going to be a little out of equilibrium
For a while. And then I think
With-
they wiggle about it.
But if this was like a rare channel, then you could imagine it might like deviate, more. It was sort of related to my question as
I could argue it's not a rare channel in that the distribution of postburst ages for these within a gig a year is actually, closer to within half a gig a year. And if you ask, how does that compare to the number of red dead galaxies in the appropriate mass range in the nearby universe? You don't have a problem making half of them this way. I mean, you haven't. The most massive ones you don't make this way, but the numbers aren't crazy for this to be an important sequence.
Good question. So at the beginning of the talk, you said, the paper that Thomas and I wrote about 2 out of 5 QPEs
Yes.
back then were post-starburst. You said we have to be cautious. Is there something we did that was not technically correct? Or
No. That was not meant as a criticism. It's just if all one has, and we've, worried about this with our samples as well. Typically speaking, the Sloan fiber is 3 arc seconds.
Yeah.
If the galaxy is within 0.05 in redshift, then we've run dumb models that have shown that aperture bias starts having an effect on your ability to accurately classify galaxies, particularly in the sense that you miss star formation at large radii and you call something a starburst galaxy, a post-starburst galaxy where in fact it's happily forming stars still. So the concern is going back to the MUSE data, right? Looking at the long slit data, looking at IFU data, manga data, where it exists for galaxies like this, and really trying to understand that issue. Because when I talked before about the other kinds of post-starbursts, the ones that have a ring, post-starburst, you would not find those. And then you would mischaracterize as post-starburst those that have extended star formation throughout the disk. They might have a post-starburst-like core, but as a whole, they might not be post-starburst galaxies. And so the question is, how connected are they to the types of samples and things I'm talking about now?
So the sample that you did with TDEs, was it based on the core or was it based on the whole galaxy for the TDEs?
That was based on the whole galaxy, and the TDEs are at higher redshift, so we're eating more of the galaxy and the fiber. So we think it's a fairer analysis. The problem with it's not a problem. The QPEs are hard to detect, so they've been detected locally. And the question is, what selection effects that introduces? Does it make you more likely to find them in dwarf galaxies just because you don't see any giant galaxies nearby, and therefore estimate their black hole masses to be very low, where they might actually have a broader range? And are we characterizing the properties of their host galaxies accurately, given that we're only looking down in the very center of those galaxies, if all you have to get a spectrum, an optical spectrum, is a fiber?
Yeah, so
But that's why the long slit data.
So these are all data taken with Magellan. I took the data with Magellan.
Right, so the MUSE data, that's the key, right? The key is, does the post-starburst signature hold up throughout the galaxy? And that's something Thomas, well, we talked about. We should look at it.
So also earlier in the talk you mentioned like the safer 2 and liner connection.
Yes.
So what do you think is happening, especially in the context of like those kinds
Yeah, I mean, I'd love to hear people's thoughts on this, because if you actually, so again, we select against galaxies that have emission lines. So the only way we put one of these galaxies on the BPT diagram is after we've subtracted our best fit to the stellar continuum, and if we see residual lines. So we're already talking about very low luminosity, whatever they are. But if you take the ratio of those lines and you put them on a BPT diagram, the vast majority end up either in Seaford 2 or liner territory. And I mean the vast majority of the host galaxies of tidal disruption events. So there is, I don't know if liners are necessarily nuclear sources. People can argue about that. But in the cases where there's evidence for Seaford 2, I mean, there's clearly something going on in the nucleus that may or may not have anything to do with the tidal disruption event. And I, of course, worry that, you know, about our ability to call something a tidal disruption event when that happens.
As in, it could be an AGN flag.
Yeah.
Well, the other thing.
I don't think we know, I mean, I'm sorry,
No, go ahead.
I think the problem in my mind is there's so much overlap in the properties of AGN, when you get to changing look AGN, when you get to all sorts of weird AGN, there's so much overlap in their properties with what we call TDEs. It's a very tough question in that area of overlap. And I think, again, this is where having much larger samples are really going to help us, both of the, you know, all manner of AGN and what we've been calling tidal disruption events.
Yeah, I was just thinking that if, so the narrow line region, I don't know exactly in the dwarf galaxies, but I guess the light travel timescales are comparable to the 4 years. We're basically seeing
Sure.
potentially the previous TD
Right,
rather
right.
than this one.
Right, I mean, I think that's this question of, you know, if a galaxy is good at having TDEs fall into it, you know, it might be a good place to look for the next one. It depends on, you know, the rates seem to be much higher, you know, factors of 10 or 100 times higher, at least in these post-starburst galaxies. So you'd expect multiple TDE events, not over a graduate student lifetime, but hopefully, but you know, they're interesting. You look at a lot of them.
This is, I guess, related to that last part where you're trying to, or you have students who are trying to determine where look for TDs just based on the galaxy properties. Could you do something where you also take into account the other types of transients you would expect to find? Because I could see that maybe helping you determine if something's more driven by like stellar concentration versus some sort of dynamic situation. Or I don't know.
Sorry, say that one more time. So
like if you see a lot of type 2s, you're like, oh wow, there must be young stars here. So maybe the reason we're seeing TDEs in this galaxy is because, or TDEs in galaxies like these is because of the stellar concentration as opposed to the dynamics of something. I could see there being some correlation.
Yes, so you're saying it would be very interesting to, if our objective is to supply, say, the LSST alert broker
Sure.
with a probability distribution across astrophysical transient types for every galaxy LSST will observe in advance, right? In advance of any, that's the dream, in advance of any transient discovery. Then in cases where that is predicting equally probable, you know, your supernova and a tidal disruption event, it might be interesting to interrogate those objects.
Yes,
That's what you're saying, because that's implying it can't tell the difference between the type of host
right.
that a supernova,
maybe
has
it's
and the type of host the TDE has. Yes.
Starburst as opposed
Yeah,
to.
I agree. That's that this interrogation of whatever these connections are arising from, I think is really interesting.
Just again, you said this, it can be challenging to get false alarms between TDEs and some kinds of funky
Yes.
AGN flares or something like
Yes.
that. So when you look at presumably these E+A, post-starburst galaxies, also the same gas that's fueling, star formation is fueling
Right.
the AGN. Do you do cuts to throw out?
So
Active
that's the
hosts,
nice
and then
thing.
are those cuts going to bias your TDE ranks?
exactly. I think that's a really good question, but I think again, in the era where there are going to be thousands of these, you can do those cuts, right? You'll know in advance which people, which galaxies people think are stable AGN. And then you're going to just eliminate them right off the top. And then you're going to end up with very weird AGN that end up confusing you potentially with the TDEs. And it's at that point, hopefully you'll have the statistics to start an in-depth analysis of, is there something that, whether it's using machine learning or not, enables you to separate those two things that's pointing to differences implicit in their host galaxies. And I think that's a really interesting question. If they don't come out different, it's a little worrisome.
Yeah, so I guess if we have any more questions, we can ask in the discussion this afternoon.
invade the QPE discussion.
Thank you for making crowd.
Yeah, that's-